Okay, good. Took a while to write. So essentially, what we do is we start off with k arms, right, and then in the first round, okay. So median elimination is going to proceed in rounds. Okay, in the first round, we pull each arm some number of times, right, determined by this magic quantity. So can people read this magic quantity? It's 1 by epsilon L by 2 the whole squared. Better? Log 3 by delta L. Okay. So I pull each arm that many number of times, okay, and then I estimate their empirical value, right, QLA I will estimate, right, where L indicates that this is the Q function I am forming at the Lth stage. Okay. Then what I do is I take these QLA, arrange them in ascending, descending, whatever order, I find the median. of all these arms, and then eliminate all those arms whose values is below the median. Right, I am eliminating. So, this is the set difference. So, I take my current set SL, right, these are all the arms that are under consideration. So, S1 will be all the arms, and then I am eliminating all those arms such that, so my QLA is less than ML, where ML is the median at the Lth level, right, and then I change my constants by magic amounts again. So, my epsilon L plus 1 becomes 3/4 of epsilon L. Epsilon L itself started as epsilon by 4, okay, now it becomes 3/4 of epsilon by 4, and my delta L plus 1 becomes delta L by 2, which already started as delta by 2. So, it becomes delta by 4 and L equal to L plus 1, and I keep going until my SL becomes 1, the number of arms left becomes 1, right. So, how many rounds will I go? Log k rounds, because every time I am eliminating half the arms, right, because I am looking at the median, I am eliminating everything below the median. So, I am guaranteed to eliminate half the arms in every round. So, I will end in log k rounds, okay. But the trick to proving any kind of sample complexity here is to show that, okay, this quantity, right, when I sum it over this log k rounds is some bounded quantity, right, and that gives me the sample complexity I want. I already told you what the sample complexity is going to be. What was it?
Order
k by epsilon squared log 1 by delta, some constant by delta. So, as far as order notations we can ignore the constant. So, log 1 by delta. So, that is what is going to be the sample complexity. So, I will have to show you that first. Second, in fact, first I will have to show you that this is actually a pack algorithm, right, that it actually gives you a epsilon optimal arm with a high probability, right. It becomes a little tricky here because I am eliminating half the arms every time. So, now I will have to think about what is the probability that I have eliminated all the epsilon optimal arms, right. So, I have to in some round along the way before I reach the final round, okay, I should not eliminate all the epsilon optimal arms, right. So, what we will do here is, you see that, right, because at the end of the thing if that one arm left is some epsilon optimal arm I am safe, right, but if along the way if I eliminate all the epsilon optimal arms then I am in trouble, right. So, what I will do now is to show that at every round the probability of me doing that is very small, so small that when I add up the probability of me eliminating across all the rounds it is still below delta, right, it is still below delta. So, that is essentially what I am going to try and show. Did that make sense? So, at every round the probability of me eliminating all the epsilon optimal arms is small, so small that when I add it up across all the rounds it is still less than delta, okay. So, that is essentially what I am going to show. Okay, so first theorem that I will state it, but I will come back and prove this later, is the median elimination algorithm which takes epsilon delta as an epsilon delta pack with okay. So, we will prove this in two parts. The first lemma will help us establish that, okay, and then we will have another result later that will help us establish the sample complex. The sample complex is actually trivial, right. If you think about it, it is essentially summing this quantity up, right, starting from epsilon by 4 and delta by 2 and successively changing the value of epsilon and delta, okay. It is just a bunch of algebra, right. You just move numbers around and simplify things, you will get it. Conceptually there is nothing deep about looking at the sample complexity. So is that clear? So I essentially have to sum up this quantity, right, for every arm. So this will be multiplied by the size of the arms, which will start with k, and then it will become k by 2, k by 4, successively it becomes smaller and smaller, and likewise the epsilon and my delta also become smaller and smaller. So the idea is to just to sum it over L, this quantity, and then replace this by a function of epsilon and L. You can replace epsilon L, right, by a function of epsilon. So what is epsilon 1? It is epsilon by 4. What is epsilon 2? 3 by 4 into epsilon by 2, epsilon by 4. Epsilon 3 is 3 by 4 the whole squared. So epsilon L is essentially 3 by 4 whole power L minus 1 into epsilon by 4, right. So like that, so you can write the similar expression for delta and you can essentially simplify it, right. So that part is fairly straightforward. So if you have time, I will just give you an intuition into that, but otherwise you can work it out easily. The first part is one that requires some work, right. So this is what we will do for every phase L. In the median elimination algorithm, we have the probability okay. So this requires a little bit of thought. So what I am saying, so what is this? This is the true best arm at level L, right. So at level 1 I would expect this to be A star, right. So right, the true best arm, I am not talking about the capital Q, right, I am talking about Q stars here. So I am talking about the true best arm, right. So in this case I would expect the true, this should be Q star A star, right, in level 1, but in level 2 itself it could be something different, because I might have lost A star in the first round itself, right. What I am saying is, okay, this is the best I could have done in the Lth round, right, potentially, right. And what is this? This is the best I could have done in the L plus 1th round, right. So the bad case is when this is less than that, right. That means I have eliminated some high ranking arms, while all I have left are low ranking arms, right. So the bad case is when this quantity is less than that quantity, right. By how much it should be less, right, that is a question, that is a trick we are asking here. So if I add an epsilon to this, so essentially I have my I don't know, let us call this J star, right, that is a maximum in the Lth level. So I have my Q star J star here, right, and I have my Q star I star here, which is the guy that gives me the max here, right. If I add an epsilon to this, if I add an epsilon to this and this is within that, that means this is epsilon optimal when you consider against that, right. Do you see that? If you add an epsilon to this lower value and the higher value is actually less than that, then it is an acceptable situation because the lower value is within epsilon of the higher value, correct. So this is a good outcome. So I am saying the probability of the good outcome is at least 1 minus delta, that means the probability is high, okay. Does that make sense? The probability of the good outcome is at least 1 minus delta, okay. Now the thing to notice here is this is not truly epsilon, this is epsilon L, right, and this is not delta, this is delta L. So why is that the case? Because every round I will lose epsilon L, right, at most epsilon L, right. So at the end of the day I should not have lost more than epsilon, correct. So what I am going to show you is that every round I will lose epsilon L, and my epsilon L is chosen such that even if I lose the epsilon L for every L, my overall loss will be epsilon, right. So that because we know that when S in S1 the best term is A star, right, and if my overall loss is less than epsilon, then at the end of this I will have at least one epsilon optimal arm left, okay. So that is basically what we are trying to show here. So this relation makes sense why we are trying to show this, okay. And likewise this 1 minus delta L is there because at the end of the day if all the events hold true also my probability must be at least 1 minus delta, right, therefore we use delta L, and that is the reason your epsilon 1s and delta 1s are already smaller than epsilon and delta, because if I start off with epsilon here and delta here I am gone, okay. So people know what W log means, right? Without loss of generality, I am going to consider L equal to 1, right. So whatever results I show here will hold for the subsequent L, right. So we start off by looking at the event E1 which is first thing I am looking at is I am grossly underestimating the true value, right. I mean this should now start looking familiar to you, because in everything we have been doing the same thing. We start off by saying okay, first thing that has to go wrong is I grossly underestimate the true optimal actions value, and then we will think about okay, what happens if I overestimate the suboptimal actions value, but I start off by saying okay, grossly underestimate this, right. Okay. So now what is the probability of this? No, and we already have our magic number here, so substitute everything and tell me. So you have the expression here, right, and you have the magic number there. That this guy will get cancelled out. Again, do you have a 4 problem there? Yeah. So well, the square should be outside. I mean, I am just writing it down from the algorithm here, so their results are wrong. Right. So it should be epsilon L squared by 2, not epsilon L by 2 the whole squared. Okay. And this is a one-sided bound. So the outside 2 will not be there, right. So everything will simplify and you will get delta 1 by 3. Okay. This is the first event. Suppose it does not hold. Okay. Suppose E1 does not hold. That is essentially I have not made a bad mistake underestimating the best arm, right. And since it is maybe I should have done it slightly differently. I have said without loss of generality consider L equal to 1, but then I put in A star here, which actually violates the without loss of generality part. Okay. So the A star here is actually the best arm left at level L. That is how you should think of it as. It is not the overall best arm, whatever be the level L, it is a best arm left at level L, and for L equal to 1 it happens to be A star, the true A star, right. For L equal to 2, 3 and 4 this will essentially become the best arm at that level. So I will just put a L there so that you know what I am meaning. Okay. So it is the best arm in the Lth level, that is left among all the arms, that is left the true best arm in the Lth level. Okay. Good. Okay. So next I am going to look at the probability that this translation is killing me. This one?
Put the 2 in the numerator.
I should put the 2 in the numerator, is it? What do you need for it to cancel out? Epsilon. Epsilon 1 by 2. So epsilon 1 by 4 half. No. Yeah. So this is epsilon by 2. So substitute that. I get epsilon squared by 4. Right, that will become half. Right, that is 1 by epsilon squared by 2. So it will get, things are all fine. Okay, good. So I am going to look at this problem, right. So sorry, not this. Okay. So E1 does not hold, that means that this is true, right. So E1 is the event where I have underestimated it. So I am saying E1 does not hold, that means that it is no longer an underestimate. So this is my estimate is within epsilon by 2, right. But then I am looking at the possibility that yeah, so that my some jth arm which is not epsilon 1 optimal, right. So that's a condition.
So it should be condition of L minus 1.
No, on L. Right. So I know that my current estimate in the Lth round, I am going to decide about eliminating in the Lth round, right. In the current round, I have not underestimated my A star L. Okay, so I am within epsilon of that, within epsilon 1 by 2 of the true A star value, right. But then I take some other arm J, which is a bad arm, bad in the sense J is not epsilon L close to A star L, it is a bad arm, right, and I figure out what is the probability that the Q estimate for that arm will be greater than the Q estimate for the A star, right. So if this happens, right, then there is a chance that A star will get eliminated, right, only a chance. Why? It has to be in the lower half, not just get beaten by one guy, but it has to be in the lower half of the arms, right. So I need at least k by 2 or whatever the size of SL by 2 bad arms to beat me, correct, for me to eliminate this arm, right. I need at least half of the arms to beat me, not just one arm, right. But before we go to that part, so what is the probability of this happening? Well, so this conditioning tells us that QL A star is not too bad, right. So what does that mean? QLJ has to be more than epsilon by 2. So you remember that figure we drew, right. So either this has to be underestimate, well, if I erase the figure, but either the A star has to be underestimated by more than epsilon by 2, or the A prime has to be overestimated by more than epsilon by 2, right. Here we are conditioning it on the event that A star is not underestimated by more than epsilon by 2. Therefore, J has to be overestimated by more than epsilon by 2, right. Since this event we have conditioned it as false, so that event has to be true, okay. So what do we get in that case? Same thing here, right. So I am kind of skipping a step here, but people are all fine with that, right. I am rewriting this bound, right. So essentially you will have to now replace this with overestimating by epsilon by 2, right. In fact, I should probably just make you write that missing step as a homework, so that I am sure that people are all comfortable with the notation, nothing more. The notation can get really complex, otherwise the concepts are very simple. That is why I am taking so much time talking over it, right. If I could just write the proof and leave it at that, because it is fairly easy, these things are fairly easy. So this is for one arm, right, and like this I have k arms, right. So the probability good. So let I don't know, we will use the same symbols here, which I do not agree with. Let hash bad be the number of bad arms, okay, hash bad be the number of bad arms such that this condition holds, right. Hash bad be the number of bad arms such that that condition holds. So these are the number of bad arms that are beating the best arm. So what will that expectation be? Huh? Mod SL by 2. Yeah, not really, but I agree with the mod SL part, but not SL by 2. I have a probability for that happening, right? And how many such experiments I mean actually is mod SL minus 1, right? Potentially everything other than the best arm could be a bad arm, right? At maximum thing is SL minus 1, right? And so it's SL minus 1 into delta 1 by 3. So that's the probability of one arm being bad, I mean one arm actually for which this first relation holds for one bad arm, and there are SL minus 1, I am just making it SL to make our life easier. So SL such bad arms, so the expected number of bad arms will be SL into delta 1 by 3. Right, now I want to look at the probability that hash bad this is where we are going to use the Markov inequality, right. So I already written the expectation here. So I am asking you the probability of x greater than or equal to a, it is the expected value of x divided by a, right. So this is less than or equal to the expected value which is divided by a okay. So what have we shown there is that if E1 does not hold, if I am good in my estimate for the best arm, okay, the probability that half the I mean so many bad arms will beat me is bounded by 2 delta 1 by 3, right. But I am also considering E1 as a bad event, right. E1 is also bad because I have my estimate for the best arm is really bad, you know. So all bets are off in some sense, right, because I can't really identify my best arm because it is so bad, right. So all bets are off. So E1 is also a bad event, right. All of this is bad and E1 is also bad. So what is the total probability of something bad happening? The two together, but they are use the union bound. If you want to use a fancy term, we use the union bound and then we say the probability of something bad happening is bounded by delta 1. Right. So this bad is delta 1 by 3, that bad is 2 delta 1 by 3, and this is actually the complementary event of E1. In fact I can just add the probabilities, I do not really need the union bound. So the total probability of something bad happening is delta 1, right. So that is essentially what we are started off by saying here. So the probability of good is 1 minus delta. Now we have shown that the probability of bad is delta L, so the probability of good is 1 minus delta L. Okay. Great. So one of the nice things about the median elimination algorithm is that it was one of the earliest papers to introduce this kind of a round based algorithms to the bandit literature, right. Now a lot of later improvements on both the regret based case and people trying to play around with the pack guarantees, all have switched to some kind of round based ideas, you know. So you do a certain number of pulls and then you eliminate a certain number of arms, right, and then go back and pull the remaining arms some more and then eliminate some more arms. So this kinds of round based elimination methods have become very popular in the bandit literature, and the median elimination is one of the earliest such round based elimination approaches, and after this it became very popular and a lot of papers started being written using this kind of a round based idea, right. So we have so far what we have shown is that it is, have we shown that it is pack? Huh? What is it? Oh, that is fine. I mean that I have already spoken about. This lemma is taken as proved, right? This lemma is taken as proved. Yeah. So you have to still use the union bound for every round that I am eliminating, right? So what I have to show is, well, I have all these deltas, right? So you have to keep adding them up to make sure that eventually you are less than, overall you are less than delta, right. Okay. So every round the probability of failure is bounded by delta 1, right. So for the k rounds the probability of failure is whatever the log k rounds, the probability of failure is bounded by summing it up. So delta 2, delta by 2, delta by 4, delta by 8 and so on and so forth until you reach 1, right. So that is the summation, and or not until you reach 1, until you reach log k rounds. So you will get delta by 2 power log k, okay, and the summation of that will go to delta, right. It is essentially delta into half plus 1/4 plus 1/8, right. If the sum runs to infinity you will get 1, but the sum is not running to infinity, it stops at some finite time, so it will be less than 1. So the summation will be less than delta, proved, right. So some probability of something bad happening will be less than delta. So likewise you can show the same things for the epsilon, right. So at every level you drop at most by epsilon L, right. So the total you would have dropped is epsilon by 4 plus, so it is essentially 1/4 plus what is it 3/4 into 1 or yeah, right. So epsilon by 4 into 1 plus 1/4 and so on and so forth, right. 3 by 4 L minus 1, yeah. Yeah, that was also upper bounded by 1 if you run it to infinity. No, it's up, yeah, it's upper bounded by 1 if you run that summation to infinity, but you are stopping at some finite amount, so it will be less than epsilon. Okay, so both of that are satisfied. That is easy enough. The harder, the trickier part is to show the sample complexity. Okay. It's not hard, it's just algebra. Can I let you guys do it, or you want me to do the sample complexity part of the proof as well? No, is it? Huh? Depends. Huh? Somebody say depends. Depends on what? That's a paper.
No, is it there in the paper?
It is there in the paper.
Then it's
Yeah, yeah. It's there in the paper. You can look at it. And so I'll stop it here for the pack complexity. We'll come back to all of this regret and pack and everything when we look at the full RL problem at some point. But right now for the bandits, I'll stop here.